I will begin with a word of prayer. Once I get up here. Dearly Father, we thank you for this day again. I thank you for this class and this opportunity we have just to study your creation. Help us to glorify you what we do and understand a little bit more about quotient manifolds and also just Euclidean geometry learning. In my prayer, Lord Jesus. Amen. So I just wanted to say a few words about chapter 21 here in John Lee's book. As he says, the main event for this chapter is the quotient manifold theorem. And so the idea here is to talk about you've got a manifold M, and it's acted on by a group G, all right? And you can define a quotient map. Pi is a quotient map from M to M by G. Now, what does that mean? So, so he defines G dot U equal to G dot X, such that X is an element of U. This is like the orbit of the set U by G. And anyway, so this lemma 21.1, he argues that for any continuous action of a topological group G on a topological space M, the quotient map is an open map. Now, I guess that, what's an open map, you know? So let's see here. The excuse me. So this is an equivalence relation, and to be more specific, here's the equivalence. P is equivalent to Q on M for P and Q and M. If and only if what? What's the condition? There has to exist G in the group such that what? Such that G acting on P is equal to Q, right? So basically, you take your manifold and you divvy it up into subsets which are connected by the group action, all right? So, you know, so for example, if we're talking about the plane, you know, then if we were to say, GB, let's say SO2, those are rotations in the plane, yeah? Then if you think about that, any point here, right, is connected to all the other points which are the same distance from the origin, right? So the orbits are literally concentric circles, and the origin is an orbit, right? So, you know, what is this isomorphic to? Like, you can probably figure it out. It's going to be like, this is, you can identify it with 0 to infinity, right? Where, you know, the representative for each circle is defined by the radius. If you throw out the origin, and you quotient by this group action, the natural group action of SO2 acting on the plane, you get, you know, 0 to infinity. That's an example of the quotient manifold theorem. I suppose. Well, all right, so some examples of smooth group actions. Include, so here's one. He's like the trivial action. M a manifold, and just defined to be G any group, G any group, man. And here's the definition. G dot P equals to P for all P and M. Yeah, M is a manifold. G is any group. Define the group acting on the manifold by this very stupid rule. It will satisfy the axioms. What are the what are the orbits here? So like the so like basically P is equivalent to Q if and only if P equals to Q, right? So like the equivalence classes of the equivalence relation here are just 1 point, they're just singletons. And so in this context, M mod the equivalence is just M again. It's a stupid version of M where you're replaced all your points with singletons which contain the point, right? I mean, it's like literally it's a set of sets. Anyway, dumb. So, but nevertheless, the orbits, so this is the orbit space. And is the orbit space a manifold? Well, yeah, because M is a manifold. All right, so there's a positive example. Another relatively simple example he gives here is action of Rk equals G on the manifold formed by Rk cross Rn. And the rule is just this. We let V act on x comma y according to the rule V plus x comma y. So in that way, we can let Rk act on Rk cross Rn. What are the orbits here? Like if you had x comma y equivalent to x bar comma y bar, what would that mean? That would mean that there exists a vector v, right? Such that x comma y is equal to like x, let me write this, x bar y bar is equal to like x plus v comma y, right? So all that would mean is that y is equal to y bar, right? Y is equal to y bar and x is free. So the equivalence, the orbits are labeled by y, and every one of them is like I'm trying to think of how to say this. So the equivalence class containing xy would be equal to like x comma y, such that x is an element of Rk, right? If I've done this right. So what would that mean if we take M? What would M mod G here be? Like intuitively speaking. So in M mod G, we're thinking of the equivalence classes. This is like a point in this space. So the points in that space are just labeled by y. So y is from Rn. This is basically just a weird way of thinking about Rn. But it also is very satisfying because if I wrote this more explicitly, I'd have Rk cross Rn divided by Rk, so the Rk's cancel and just leaves you with Rn. But nevertheless, again, the orbit space is a manifold. All right. Then he, I won't write the other ones down, I'm just going to talk about them. He then talks about if we take the complex plane and we let the unit circle act on it, by, like if you take the complex plane and let it act on by the unit complex numbers, then that's just this example. The orbits are circles, And so actually his example C is pretty much my unnamed example. And then he gives a more dramatic example. Now, by the way, this, not a manifold. This is not a manifold. I don't think that's true, though. I think this is a manifold with a boundary. I don't know why he says that's not a manifold.
Do we have an equation for it?
What's that?
I guess we would, right? Have an equation for it.
Well, this is like a one-dimensional half space. That's a manifold with boundary. So I maybe missed the context of why he said that didn't count. Anyway, let me go on here. So example E. Well, actually, excuse me. I'll just make it 3. If we let GLN act on Rn by the rule, you know, A comma X maps to, well, my bad. I just want to say A dot X equals to AX, right? What are the orbits in that case? So the orbits in this case, where does 0 map to? So like A dot 0 is equal to 0 for all A, right? On the other hand, you can construct, you know, if you have X and Y in Rn without 0, then there exists A in GLN such that what? Such that A times X is equal to Y. So basically the orbits of the general linear group on column vectors, either you have the origin or everything else. So like, if I think about Rn, mod this group action, I either have, you know, basically I've got 2 things. I've got, you know, the origin and everything else. Those are the orbits. That's not a manifold, right? Well, anyway, it's certainly not a. I guess you could say it's a 0-dimensional manifold, but let me move on here. So I'm really just trying to hit the high points here. So the quotient manifold theorem says the following. Quotient manifold theorem says that suppose G is Lie group acting smoothly, freely, and properly. Smoothly, freely, and properly on smooth manifold M. All right. Then the orbit space M by G is a topological manifold. Topological manifold of dimension M minus dimension G. And it has a unique smooth structure. There exists unique smooth structure with property that the quotient map here, pi, from M to M by G, is a smooth submersion. All right. Now, I had really hoped that by the time we got to this part in the course that Dr. Sprano would have covered the quotient topology, but I don't think that happened. So I really can't make good on explaining this more deeply in here at the moment, unfortunately. All right? But this ties together with something called the quotient topology. And I mean, to explain it to you in a nutshell, the quotient topology, guys, is the one that forces like the quotient map to be an open map. So like, no, I'm not gonna, I mustn't, maybe another day, but I'm not ready to have that talk with you guys today. So I should behave and not do that. An example of this, let's see here. So example 1, if you take Rn and you mod by Zn, all right, that gets you something that is homeomorphic to the N torus. So I can picture it like, here's a picture in the plane. I can't draw anymore, but in the plane I can picture it. So here's, x1, or here's x, here's y, right? What is, so this, I'm talking about the natural action of the integer lattice under addition. So where are the integers in the plane? Yeah?
When you did, there exists exclamation mark unique. Okay, unique.
Yeah, there exists unique. So here, here's the integers, let's say. There's lots of them, right? There's a lot of them. And they're spread out, though, aren't they? Yeah? So the thing is, an orbit of a point under the integer lattice addition, right? If I take, for example, this point, let me use a different color. Excuse me. If I take, for instance, this point right here, right? Then the orbit of that point is a whole grid of points, right? Like the orbit of it is this, and this, and this, and this, this. So if you think about all this, if you just want to keep it, you can basically trade this mod this for just like a fundamental cell. A fundamental cell, all right? Where all four of these points on the end here are in the same orbit. See, so in this quotient, all four of these points are identified, right? And also, like this and that are identified because they're just shifted by, 0, 1, which is in the integers. And these are related by a shift of 1, 0, which is in the integers. So the way you can denote that is like this. This guy is the same as that guy. This guy is the same as that guy. Maybe I think usually they use like 2 marks. So this is code for these are identified, these are identified. And if you can envision that, right? If you can imagine taking a smooth sheet of rubber, cut it into a square, and then you imagine taking the 2 ends, connecting them, and then if you can imagine morphing the other 2. If you can use your imagination, you can see a torus here. That's what I'm trying to say. I can't explain it, but that's good. That's what it's for. You see the donut? That's what it's for. That's what it's for.
I see a very long, very wide donut.
No, very wide. Yeah, yeah. So his example. So this is on page 550 of John Lee with more details, of course. And the other example he's got there is if you look at the 2-element group. You can look at the 2-element group, which is just like plus or minus 1, and let that act on S2. So like if you look at the sphere, you can let it, G equals to minus 1 and 1. So that'll take this point X and maps it to that point minus X, right? So if you take S2 mod this group, it's RP2. Right? That ends up being RP2. But this works for Sn, so you can actually trade my 2 out for an n. Sn mod this 2-point group gives you a model of RPN, which is pretty cool. All right, let me go on here. I don't want to spend all class on this stuff because I'm not really telling you much. So, I would just tell you guys, you can look at page 553. I'll read the results, right? So like, if you look at the natural action of orthogonal group on the n-1 sphere. So if you think about a sphere, right? If you think about a sphere, you can rotate points on the sphere and you'll stay on the sphere because the rotations maintain the distance from the origin, right? So there's a natural action of rotation groups on the sphere. And the orbits of those will maybe give you like circles on the sphere or something like that. I'm not sure exactly what happens actually. Well, here he tells us though. He says, consider the natural action of ON on Sn-1. If we choose our base point to be the north pole, it's easy to check that the isotropy group is On-1, thought of as orthogonal transformations of Rn that fix the last variable. Thus, Sn-1 is diffeomorphic to the quotient manifold On by On-1. So this is explained, for instance. Let me write it down. So S, the n-1 sphere, you can understand as being obtained by the quotient of On by On-1. And the way that's going is it's like, here's it, like geometrically, let me talk about what this looks like. So like the 2 sphere, right? I can actually picture this for the 2 sphere. So like the 2 sphere looks like this, right? Here's the North Pole. Here's the South Pole. All right? And O2 is like rotations. So if you take rotations that fix the North Pole, the rotations are like this. And apparently, you can understand this as like S2, you can understand as like O3 mod O2. No, I can't picture O3 mod O2.
You do S1 equals O2 mod O1.
Right. That's also true. So this is harder to picture because what's the dimension of O3 as a manifold? Well, the Lie algebra of it is just antisymmetric 3x3 matrices, I think. So it's, oh man, dudes. Oh, yeah. Well, anyway, I think that's 3-dimensional. I think O2 is actually 1-dimensional, so it makes sense, but anyway. My point to you is simply this, is that a lot of the manifolds that you know and love, you can obtain as being diffeomorphic to the quotient of 2 Lie groups. And the spaces that appear in this way are called homogeneous spaces. And there's much more to say. I just wanted to give you a sense of it. You should read this chapter. It's an important thing to know about. Maybe you'll get to take a whole course in it in grad school, Now, there is this word of caution, though, on page 554. He says, because homogeneous spaces have such rich structures, it's natural to wonder whether every smooth manifold can be realized as the quotient group of a Lie group modulo a closed subgroup, or equivalently, whether every smooth manifold admits a transitive Lie group action. The answer is emphatically no, because there are strong topological restrictions. He says, in the first place, it's a simple necessary condition for a disconnected manifold that all of its connected components be diffeomorphic to each other. That's one thing. But more significantly, a remarkable 2005 theorem by G.D. Mostow shows that a compact homogeneous space must have non-negative Euler characteristic. So this is actually a pretty strong topological restriction. Homogeneous spaces are special. Not every manifold is a homogeneous space, but many ones that you know and love are. So it's something to be aware of, because if you can view the manifold as a homogeneous space, it means you can use techniques of group theory to understand certain aspects of it, because these are like both matrix groups, and it's just a very nice thing to think about. And the theorem that if you have a Lie group, G, and you quotient by a closed closed sub-Lie group. This is, diffeomorphic to a manifold. That's a very nice theorem. It's a very nice theorem. Here the action is simply the so-called coset, like coset multiplication in the group is the action here. And that's still true. The thing that makes it so interesting is it's still true in the case of like discrete groups. So like a closed submanifold of dimension 0. This is an example of this. This is an n-dimensional manifold. This is a 0-dimensional Lie group. Actually, this is itself a Lie group. That's a subgroup. Notice that? Well, you haven't had abstract algebra. How would you notice? But this is a group with respect to vector addition. This is a subgroup of Rn with respect to vector addition. This is, in fact, a discrete subgroup of Rn. And this is an example of that theorem. N-dimensional mod 0-dimensional gives me n-dimensional. Nevertheless, this is a somewhat more interesting n-dimensional space than that one, because it like loops back on itself, among other things. So, what's that?
Got it.
You got it? Here's the church, here's the steeple. What are we doing here?
Donut.
Oh, that's your donut. All right, cool. All right, well, now that I got chapter 20 out of my system, and it only cost us 26 minutes and 40 seconds, yay. Let me go on here. So begins the hard segue to the rest of the course. So the rest of the course, for you guys, I will be presenting you a lean mean version of elementary differential geometry, because it has occurred to me as we've gone on in here that you guys need more examples of just basic differential geometry and how that all works, right? So if I had to do it over again, I would have started with this and then transitioned to manifolds like 3 weeks into the course. But better late than never. See, because I could go on to the abstract later chapters in John Lee, but I don't think it's going to stick with you if I do. I think that if you can understand what I'm about to tell you, these things will have lasting value in the pantheon of your mathematical ideas. Thank you. So the things I'm about to teach you are, roughly speaking, taken from a classic book by one of the best differential geometers probably ever to live. Well, I don't know, maybe that's too strong, but he was very good, and he wrote wonderful books. His name was Barrett O'Neill. And so let's just get into it. Let's talk about isometry, and Euclidean geometry. So, you know what Euclidean geometry is, right? So, in particular, no, it is incorrect. It is Rn with, dot product. That, in a nutshell, is Euclidean geometry. It's Rn with the dot product. But more specifically, excuse me, definition here. This will give it a little more texture. F, a mapping from Rn to Rn, all right, is an isometry. It's not really that. It's Rn with the usual distance function as defined by the dot product, right? So F from Rn to Rn is an isometry if the distance from f of p to f of q is equal to the distance from p to q for all p and q in Rn. Now, I guess I owe you guys a definition of distance, right? Probably should do that, shouldn't I? So I said Rn with the dot product, but the truth is what I really mean is the distance from p to q is the square root of, q minus p dot q minus p, right? That's how we define distance in Rn. Okay. And that will indeed define a metric in the sense of topology that you guys are taking, as you well know. Theorem. F and G in the, let's call it isom of Rn. The group. Oh, I said the group. Is it a group, though? Is the set of all isometries a group? What do you guys think? You're like, well, you're calling it a group, so odds are probably for it. But here's my first claim. The composite of two isometries is an isometry. How do you prove that? Very easy, right? So the distance of F composed with G, P, comma, F composed with G of Q is what? Distance of F of G of P, F of G of Q. But what's G of P and G of Q? Well, they're just points. They're just points in Rn, right? So because F is an isometry, I can drop the F. And because G is an isometry, I can drop the G. So therefore, G composed with F is an isometry. That may be a prophecy for my next spring.
Ooh.
Yeah.
Are you teaching Matthew?
Yes.
Really?
Supposedly. So, what else? How about this?
Math 200 kids just watch your lectures on manifold theory.
Yes. Yeah, they just need to watch everything I've taught in the last year as prep, right? That's a tenable yeah, so here. How about this? So how about t of x equal to x plus a? Or we could call this t sub a. Translation by a is what this is called, right? Then TA is an isometry. Can you guys prove that? I've been so, it's been sad in here. I've proved so few things of the things we've said, you know? I miss proving things. So this is what? Square root of p plus p, oh, my bad. Q plus a minus p plus a, dot product with itself, right? Maybe I should introduce the norm notation, yeah? That would have been nicer, right? This is just norm of q plus a minus p plus a, which is what? Norm of q minus p, which, by the way, is the distance from p to q. Yeah, let us agree that we may also use the norm notation to simplify our life a bit. So there you go. Translation is a isometry. Are there others? Theorem. There are others, yes. If R transpose R is equal to I, and oh, by the way, we're stick with Rn here. You know, for an n by n matrix R, then if we define, let's say, you know, I don't know, let's call it L sub R, mapping from Rn to Rn by L sub R of x equal to Rx, then L sub R is an isometry. Last time I said a translation is isometry. Now I'm telling you a rotation is an isometry, right? Because a linear transformation which has a rotation matrix, or possibly a reflection matrix, as its matrix is a rotation, or You could say a rotor reflection, because it could be a reflection. So what's the proof? Well, here we go. So what's the distance of L sub r of P to L sub r of Q, right? So that is going to be the norm of RQ minus RP, right? Which is the norm of R times Q minus P, which is RQ minus P transpose times RQ minus P. And that's all square rooted. But then by sock shoes, you got yourself Q minus P transpose R transpose R times Q minus P, which is the square root of Q minus P transpose times Q minus P using the orthogonality condition, which of course is the distance from P to Q. Well, it was a good last action. Oh, come on. Was that a pun? Oi. We good? So we got translations, we got rotations. So what do you guys think? What is the set of all possible isometries on Rn? What do you think it is? Notice that my definition of isometry, to be clear, all I'm saying is that f is a function which preserves the distance between points. What does that imply about the function? I mean, apparently it could be a translation. It could be a rotation. Is there more? There can't be less. I'm going to show you a derivation here that I found in O'Neill's book. And, well, it's just nice. Because what I'm about to prove, if you were given this as a homework problem, it would not be easy. So here's the theorem. If f is an isometry of Rn and it fixes the origin, then f is equal to a rotation, L sub r, for some r in, On. On is the set of all matrices that R transpose R equals I, right? So here's the proof. So we start out like this. So we're assuming f is an isometry, f of 0, 0. Check this out. So the distance from f of p to f of 0 is equal to the distance from p to 0. Thus, the distance from f of p to 0 is equal to the distance from p to 0. Which implies what? The length of f of p is equal to the length of p, right? The distance of f of p from the origin is the distance of p from the origin. Furthermore, note, p not equal to 0 implies f of p not equal to 0. We'll need that, I think, at some point in what it follows. You guys with me so far? All right, check this out. So we've got the distance from f of p to f of q, square that. It's equal to, of course, the norm of f of q minus f of p squared, which is the dot product of f of q minus f of p with itself. Which is the dot product of f of q with f of q, f of q dot f of q, minus 2 times f of p dot f of q, plus f of p dot f of p. What is f of p dot f of p? What is f of q dot f of q? So that's the norm of f of q squared minus twice f of p dot f of q plus the norm of f of p squared, right? But this, of course, is equal to the distance from p to q squared, right? Which is itself equal to p dot p minus 2p dot q plus q dot q, right? Which you might recognize as the length of p squared minus 2p dot q plus the length of q squared. What does this tell us? So notice that by this, by the upper part of the proof here, this is the length of q squared. This is also the length of p squared. So look at this. What does it give us? What do we have here exactly? Those things are canceling, right? They be canceling. It just leaves us with that is equal to that. Therefore, thus, f of p dot f of q is equal to p dot q for all p and q in Rn. All right? So what does that tell us? Notice if we look at f of ei dot f of ej, what do we get? We get ei dot ej, which gives us, let's see, Kronecker delta ij. Thus, f of e1 dot 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 f of en is orthonormal basis for Rn. That's nice, right? It's a basis. So check this out, yo. We've got f of cx plus y dot f of z is equal to cx plus y dot z, which, by the way, by the properties of dot product, is cx dot z plus y dot z, which is, by the way, c f of x dot f of z plus f of y dot f of z, which is equal to c f of x plus f of y all dot f of z. Right? Okay, so take f of z equals to f of ej for j equals to 1, 2, da 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 n, and find that f of cx plus y is equal to c f of x plus f of y. We've just proved that f of x is necessarily a linear transformation. It was not assumed from the outset. We've proved that preservation of distance between points by a function forces linearity. That's just very cool. This is not, I'm not sure this is something I would have ever figured the proof out of on my own. I'm not sure. I really don't know. I feel like there's a chance I never would have got it. It's just clever, really clever. And so once you know it's a linear transformation, so f linear, then of course f of x is equal to the standard matrix of f times x, right? And if we just call that r, rx, then notice that like f of x dot f of y equals to x dot y. That tells me that rx dot ry is equal to xy, x dot y, which tells me that x transpose ry is equal to x transpose y, which implies r transpose r is equal to the identity. Because if you put x and y, if you set x and y equal to, say, ei and ej, that gives you the ijth component of the matrix R on the one side, and on the other side, of course, you've got the identity matrix. And that finishes the proof. So what do you guys think? Are there other isometries besides rotations and translations? Apparently, if the isometry fixes the origin, it has to be a rotation. In the generalized sense of also including reflections, yeah. So what's next? Well, I'll tell you what's next. Next theorem. So what's next? All linear functions are isometries. Well, that's not true. But the next thing oh no. Oh man. I've been doing pretty well today, up until just then. Now this next theorem, I feel like I have a chance. If I had the one we just proved, I think I have a chance at getting this one of my own accord. Oh, come on. So here's the next theorem. Every isometry, if f is an element of the isometries on Rn, then there exist unique A in Rn and R in On such that f is equal to T sub A composed with the multiplication by R map. All right. And really, I should say, you can replace this then with like if and only if. That might be better. F is in an isometry if and only if there exists, I should just say there exists A and R such that it's actually unique. There's the unique choice of A and R, but once I put the if and only if, it kind of ruins my language. So this direction, well, this direction is stupid, right? So if we have F is equal to TA composed with LR, then that's an isometry. How do we know that? Well, we already proved all that. Because we proved one, that TA is an isometry, we proved that LR was an isometry, and we proved that the composition of isometries is an isometry, so stick a fork in it. You got it? Oh, thank you.
It unfortunately was not on that board at all.
Did I never get that?
No, it was on board 3. I put it on that board for a second.
I think I moved over to board 3. I moved it to 3. It was at 2. I think. Well, we'll find out later. Sorry, Ernesto. Anyway, so that way is fine. How about the other way? Check this out. So, F in isometry of Rn, then F, if F of 0, let's say F of 0 is equal to A. Maybe that might be it. Then maybe I should say, well, okay, A. Let let's see here. Oh, rats. Oh no, that's not quite it. All right, let me take medicine here. So F in isometry, I said let G of x be equal to F of x. That's what I need to do, F of x minus F of 0. Then what can we say? G of 0 is what? F of 0 minus F of 0, which is 0, right? And G is equal to translation by minus F of 0 composed with F. See that? G is nothing more than the composite of the translation by minus F of 0 vector with F. Therefore, G is an isometry. It's an isometry which fixes 0. Therefore, it is a rotation. So you see this is equal to L sub r for some rotation r by our previous theorem. Consequently, if we compose, what's the inverse of a translation? Translation? What inverse, though? So like here's the deal. T of minus a composed of T of a is equal to T of a minus a, which is T of 0, which by the way is the identity. My point is that these guys cancel, and we're just left with F is T of F of 0 composed with L sub r. In other words, A is equal to F of 0, and we're done.
I like the 2 little flashes.
Yeah. And the uniqueness, well, I won't bore you with, you can prove it's unique. It's fairly obvious that it's unique because A is defined by F of 0, which is a single thing. And the rotation matrix for an isometry which fixes the origin is also clearly unique if you study our proof of what we just did, because it's just the standard matrix. So there you go, like isom Rn is equal to, f of x, well, f from Rn to Rn, right? Such that f of x is equal to a plus Rx for some a in Rn and R in On. There you go, that's the isometry group in Rn. These are also known as the, well, I think maybe I should, if I tack on the condition determinant of R is equal to 1, that would mean that that rules out unphysical inside-out transformations. Like if you have a rotation with determinant -1, you can turn a Rubik's cube like inside out. So if you want to think of these as actually actual physical motions that preserve the shape of rigid objects, then I think the group of rigid motions would be these such that the determinant is 1. If I don't force determinant 1, it could do stuff like turn things inside out. So, great. What happens then if we study how these do. Really interesting. So theorem, well, this is generally true. If we push forward under a smooth map from Rn to Rn, alpha prime, then it's going to be F composed with alpha prime. In other words, that's true for any smooth map. But we can prove, actually, that the push forward by if F is an isometry, the push forward of the, let's say, jth derivative is actually equal to the jth derivative of of that. So like if you can imagine, here I've got alpha, and over here I've got my map F, and over here is like F composed with alpha, right? Then in isometry, it will preserve the derivative of the curve, but it also naturally pushes forward the acceleration, the jerk, like all of the derivatives of the curve are transferred by this isometry. And notice that it's more than that though. See the push forward of a vector v, it's just actually equal to rv, where r is the rotational part. So what this means is that if you push forward under an isometry v, and you take the dot product with the push forward under the isometry of w, you get v dot w, because it gives you rv dot rw. So the dot product is preserved under the push forward of an isometry. All right? So when you guys took Calculus 3, so properly speaking, Euclidean geometry concerns those concepts, those propositions, those objects which are invariant in some sense under isometries. Like whatever's a geometric notion, if it's true for one space, it ought to be true for the other space, which is obtained by just like doing a rigid motion of that space, so let me put it a different way. In high school, you studied when are two curves congruent, right? What would it take for two triangles to be congruent? What do we have? Like, was it side angle side, or?
There are several.
There are several.
One of them is side, side, side.
Side, side, side? Yeah, we got that one. No angle side, side, thankfully.
Hypotenuse leg.
Hypotenuse leg. So that's a natural question to ask is, if I've got some wackadoodle curve up here, and I've got some other curve over here, are these actually the same curve? Could I take this curve and translate over here and rotate and get the same, here, I'll do it again. Very exciting. Can you take this curve and like translate and then rotate and get the same curve? Like,